In this first lecture of Chapter 3, it is split into five different lectures. We're looking at the number system as well as whole number operations. So in this first lecture, we're going to focus on the systems themselves. The goal is to be able to explain what a number system is, how it originated, and how it's related to representation with numbers and models. We want to be able to compare and contrast different number systems presented. And then the math portion of this is starting to identify place value and working in base 10 as well as other bases. And then the teaching portion is looking at issues in learning with different number systems. So here are some number systems that were developed from different cultural groups. The key here is no matter what number system you choose, there's a representation of a quantity. So it's a symbol that represents a quantity. And we call them cardinal numbers, like we did last week with the numbers of sets, because they're going to be whole number values or counting numbers. And what's interesting is if you look at the Babylonian, the Egyptian, the Mayan, and the Roman numerals, those number systems do a better job of relating the symbol to the quantity. So in Babylonian, we have one upside down triangle, which means one, two means two, three means three. We've got the same thing with the tally marks in Egyptian. And then once we get up to a certain point, we have different symbols that are used. But really in those lower numbers, and in the Mayan, you've got some basic, again, the symbol denotes the quantity. And then what's interesting is here in the Hindu, the Arabic, and the Hindu Arabic, we just have a symbol that we've assigned. So imagine if you were first giving this number system a try, maybe you wouldn't use 0 or 1. Maybe you draw a turtle and that would stand for 1. So what's interesting is these last three number systems, they don't really have a relationship between the symbol and the quantity that it represents, which is something as you're teaching students, we need to realize that this is an intuitive. Quantifying a number and an amount is not as intuitive with these number systems as it is with the earlier cultural ones. So when we define a numeration system, we're talking about a collection of properties as well as symbols that represent the numbers systematically, just like we saw on the last slide. In the Hindu Arabic numeration system, what we use, all the numbers are constructed from the 10-digit system 0 to 9. Place value is also based on powers of 10. So when we start breaking this down into place values, this will be looking at the different powers of 10 as compared to some of the older methods, and I'll talk a little bit about that when we get there. So place value, we have our ones place or our units place, the tens, the hundreds, and the thousands. So a lot of times we tend to assign these words. What we've done in some recent curriculum revisions is we're showing this as powers of 10 so that students connect the idea that 1,000 is 10 to the third. So we're trying to build a connection between what is place value and then how do we represent that quantity as a power of 10. So in expanded form, perhaps in the past, you've seen students work with, or maybe you've worked with yourself and you've said that 6,789 is 6,000 plus 700 plus 80 plus 9. So that's been the traditional representation of expanded form. What we're doing now is instead of saying 6,000, we're saying 6 times 10 to the third, because that is 6,000. 7 times 10 squared, because that is 700. So that's something to be aware of, and a slightly different track that we're going down to really push the idea of thousands is 10 to the third, 10 times 10 times 10. And that's really helpful when students start to get a little bit higher up in their math and they start looking at number operations, scientific notation, and things like that. So we're really preparing them strongly by using these powers of 10. And then we know that if a is any natural number, this is just the proof behind the 10 to the third, that a to the n would be that repeated multiplication. So 10 to the third is 10 times 10 times 10. So I'm multiplying 10 by itself 3 times. Now, a lot of times we use base 10 blocks to do math. We pull out manipulatives and different things. If you're using base 10 blocks, it's a good way to quantify because, again, a student may not know what 10 to the third is. It's very difficult to quantify those symbols with what they actually mean. So if we're looking at 10 to the 1, that would be one row of our base 10 blocks. If we're looking at 10 squared of a hundreds place, that would be a complete square block. If we're looking at 10 to the third or the thousands place, that would be the three-dimensional cube that we're using here.
Sorry, I couldn't hear what.
What is the fewest number of pieces you can receive in a fair exchange for 11 flats, 17 longs, and 16 units? So when I'm talking about units, longs, and flats, this is what I'm talking about. So if I have 11 flats, then I have 17 longs and 16 units. I know that 16 units is equal to one long piece and 6 because units is 10. So when I say 16 units, I could take and I could borrow 10 from those units and I could add a long in here. So basically, this is the process of borrowing, and this is extremely important because although it may be somewhat difficult to show kids, at this level, again, you're playing towards a higher field. So we're teaching them we can take 10 out of this because it makes one long row, and we have 6 left over. So then we have 17 plus a long, which gives us 18, and we get 11 flats. So we're basically trying to shift those over into the shortest statements, the fewest number of pieces. So then we're going to look at what can we do with 18 longs? Well, if I have 18 longs, 10 longs is one flat. So I can take 10, I can borrow 10 from this category of longs, and I can put it over here in the flats. Then I have 8 remaining. So that gives me 12 flats, 18 longs, and 6 units, and that completes my trade. So then I have the fewest number of each item possible, unless we want to take it one step further to the block. Now notice the block was left off here on the side, so some of your students may not quite catch the block in the first go, but we have 10 flats is one block, which is 1,000. So we can actually take 10 of those flats, and that equals one block. We have 2 left, and this would be the absolute fewest that I have. And you should see that none of them really have over 10 because everything is 10 from one to the next. So 10 units is one long, 10 longs is one flat, 10 flats is one block. So we're always pulling powers of 10, and that's also great for mental math for students. So when I add this together, the fewest number of pieces would be 1 plus 2 plus 8 plus 6, which would be 17 pieces. So you've got to discern in the lab what they're asking you to do. Are they asking you to give them one block, or are they asking you what are the fewest number of pieces, which means you're going to have to sum that up. So if I wanted to rewrite this as powers of 10, then I would rewrite this as 11 times 100 plus 17 times 10 plus 16. Or I could write it as 1 times 10 to the third, one block, 2 times 10 squared, hundreds, 8 times 10, tens place, 6 would be the ones place. So I'm just taking this and taking these digits and I'm showing them what their place value. Because one block is 1,000, it would be 10 to the third. Because flats is 100, it would be 10 squared. Because longs is 10, it would just be times 10. Now, with the tally numeration system, probably the most challenging thing is to get students to realize that fifth mark. So we have 1, 2, 3, 4, and that slash in the fifth mark. So a strategy you might utilize to show your students that is to automatically look for that slash mark. Once I see there's a slash mark there, I know it's 5, and instead of counting the individual tallies at that point, I can count by 5s. So then I would have 5, 10, and then I'm going to go ahead and add 11, 12, 13, and that gives me 13 total. Now, again, we want to compare and contrast these number systems. The Egyptian numeration system is going to be using these different symbols. Now, notice they're not, numbers are not powers of 10. So one of the unique things with our system that we're using here is the number of zeros does correlate to the place it falls in the number. So we have ones, tens, hundreds. That doesn't happen with the Egyptian numeral system. There's no indication of how that symbol relates to a place value. So when we're comparing and contrasting systems, that's something to keep in mind. Even though our system isn't showing 10 dots as a symbol, it does lend some help to our place value discussion. So if I was to use the Egyptian numeration system to represent that number, I'm going to be looking at, let me swap it back here. So this would be a million. This is 2 million, so I need 2 of those. it's 300,000. So I need three of these. And that's how we're coming up with this system. So it's writing the symbol. So I have 40,000. So I have four 10,000s. I have five 1,000s. I have one 100 symbol, two 10 symbols, three 1 symbols. So it's not it's more of a clear symbol, but you don't have a clear place value idea when we're using these symbols. So what's easy to know is that, oh, I have two of these. So there's actually two symbols versus just one singular symbol of the number two. If we're looking at the Babylonian system, then if we look at a triangle is 1, and then the sideways similar triangle is 10. So that if I wanted to use that system to represent this number, I would need my upside down triangle, and that's going to represent 60 to the third. Then I have my 86,400, 3,060, and I have my 10 because we know the symbol is 10. So let's take a look here. I have 1, 2, 3, 4, 5 of these plus an upside down triangle. So I have 5 10s and I have 1 1. Now, why is this number right here? Why are these, what's happening here? Because I'm looking at a different base system. So that's what's happening. This is their 10 value, this is their 1. So if I'm looking at this, I'm looking at 24 times 60 squared because I'm in base 6. So 60 squared times 24 is 86,400. This would be 10, 20, 1, 2, 3, 4. So you've got to realize the Babylonian number system is in base 10. So what does that mean? That means that I'm going to have powers of 6, or powers of 60, I'm sorry. So we're going to have powers of 60 because of the base of it. If I look at the Mayan numeration system, I'm looking at base 20. So base 20 means I always have a ones place, and then instead of 10s, I have 20. Then I have 18 times 20, 18 times 20 squared, 18 times 20 cubed. So this can get a little tricky because of the base system for Mayan numbers is very, very different. So instead of moving by powers of 10, I'm moving by powers of 20, but then I'm also looking at 18 times 20. So I'm not just really looking at powers of 20, I also have this extra layer of complexity given by adding that 18 into the base. So then I have my Roman numerals, which we're mostly aware of with Roman numerals. If you may not be, you may want to take a moment to write this down. In the Middle Ages, what they did was they put a bar over a Roman numeral, and that would multiply it by 1,000. So we know that V is 5, but if I put V bar, that's 5,000. So if I want to use that Roman numeration system, I have to represent 15,000. 15 is XV, and if I want to be 15,000, I'm going to put the bars over the top. 478. So if I go back here, I have CD would be 500. So if I took 500, or I could do 400 by taking 500 minus 100. So I have that 500 minus 100. Then I'm working with the last few digits there to get 5, 6, 7, 8. And instead of having 50, I'm taking 50, take away that amount to give me that. So this is just kind of a complex system. When you're looking at this, this is going to be definitely helpful for how you want to look at using these numbers. And remember, placement would indicate if it's before the number, that's going to indicate a subtraction. So IV is 5 minus 1 or 4. If I wanted to do VI, that would be 6, because that would be 1 plus 5. So that's where that's coming from there. If I wanted to look at a quinary, a base 5 system, then notice what I'm looking at here is I have 1, 5, 2, 5, and it's a nice base system because you can use 5 fingers, and that helps students understand the base because you're relating it to their 5 fingers. So once you hit 5, you're going to have one hand and 0 fingers, and that's going to take you over to the next place value. So if I wanted to convert this in base 5 over to base 10, I'm going to write it as powers of 5. So that if I'm in this place, it's the ones place, so it's times 1. This would be times 5, 5 squared, 5 cubed, 5 to the 4th, just like we did with the powers of 10. So I'm taking every number in its place value. So I have 1 times 5 to the 4th. I'm going to simplify that to get 625. 1 times 5 to the 3rd to get 125. 2 times 5 squared, because that's the second place value. That would be the hundreds place, right? So instead of 10 squared, it's 5 squared. And we're going to get 824. So to convert from one base over to base 10, instead of doing powers of 10, you're just doing powers of that base number, and then you're going to sum them up to get your base 10 value. The binary system has only 2 digits. So when we look at base 2, it's especially important because we use binary systems in computers. We also use it in statistics for yes-no questions. So if I'm wanting to quantify, to do a statistical study, yes, no, I'll use a binary system where 0 might be yes and 1 might be no. In the computer system, one of the digits is going to be an electrical signal, and the other one's going to be the absence of it. And we've kind of evolved past this in coding, but this is the initial intent of that base 2 system. But like I said, it is still currently used within the context of statistics. A lot of times we'll use a binary system as we're coding different surveys. So here's an example of going from base 2 to base 10. So I'm going to use powers of 2. So the ones place is always just hanging out. The tens place, instead of being 10, it's 2. The hundreds place, instead of being 10 squared, it's 2 squared. And so on. I'm going to add them all up and get 23. So in the lab, these questions are definitely ones you want to get. When I'm converting to base 2, that becomes much more challenging. When I'm becoming to base 2, I have to start doing some really fancy math. If I want to go to 27, I have this stuff going on over here in the left-hand column. So if I'm wanting to move it to base 2, I'm going to look at 2 goes into 27, 2 goes into 2 once, 2 goes into 7 3 times. So I have this I have this 1, and then I have this other 7 hanging out. So I have 1 10 place, and I have the 7 hanging out. It goes into it 3, but I have a remainder. So that's what's happening here with the 13. Then I'm going to bring that 2 into the 13. Well, 2 can't go into 1, but it can go into 12. So then I'm going to carry that 6 down. And then I'm going to have 2 goes into 6 3 times, which finally results in me getting a 1. So this is kind of a series of division problems. I don't really recommend what's happening on the left. It's very confusing. So you're going to, 2 goes into your original number. It goes into it 13 times. Don't worry about anything else besides remainder of 1. 2 goes into 6 12 times. So, 2 goes into 6 3 times. So I have the 2 goes into 3, 2 goes into 3 1 time, and then I have that 1 hanging out. So when I look at these numbers, I have a remainder of 1 from the first bit of math I did. I have a remainder of 1 from the second math I did with the 2 goes into 27. It actually goes into it 13 times with the remainder of 1, so that's where this comes from. 2 goes into 13, it can go into 12 with the remainder of 1. That's where this 1 comes from. 2 goes into 6 perfectly, so it would be 0 remainder. 2 goes into 3 1 time, and it has that remainder of 1. And then we have finally the 1, which is following up the second place. So it's kind of a combination of division and remainders. If I have 12-digit systems, we will use a duodecimal system where T represents a group of 10, E represents a group of 11, and then the base 12 digits are going to be through T and E. So basically what we're doing is we're using regular numerals all the way until we hit 10. Then we're going to convert, instead of writing 10, we're going to write T. Instead of writing 11, we're going to write E. So if I wanted to convert E to T over to base 10, we love going to base 10 because E stands for 11. It's base 12. So I'm going to have that E, that's my hundreds place because there's 3 digits. So 12 squared, my tens place typically, 2 times 12 to the 1. And then I got my ones place hanging out, and T is equal to 10. I add it all up, and I get 1618. Converting to base 10 is 100 times easier than going from base 10 to another base. So this is another example. You don't have to utilize this method, but I'm just looking at long division. How many times does 144 go into 1277? I'm using 144 because that's the power of 12. So I have 12 squared goes into that. I have a remainder of 8. Then I'm going to put it into 12 because I have my hundreds place, my tens place. I have a remainder of T. So remember what T stands for. And then I have my 1. I'm going to go into, I have 1 goes into 5. It has a 5. And then I'm back out at 0. So I get 8T5. You can organize it this way or with those little boxes you saw this way. But really, just remember, it's a count of division. And we're using place value, and the remainders is how we're coming up with these base 12 numbers. So what is the value of G? And G, 36 base 12, goes over to 1050 base 10. So I know if I have G in the hundreds place, that would be 12 squared. 3 times 12 would be the tens place. 6 times 1. So I'm going to simplify that to this statement right here. Then I'm going to combine like terms of the 36 and 6 to get 42. I'm going to subtract 42 from both sides, and I'm going to divide by 144, and that solves for G equals 7. So it's not as bad as going from base 12 to base 10 completely, because we also have this extra factor of G, but it's like solving a linear equation here. You're just going to use a symbol to represent G.